Great. How are you?
Doing all right. Doing all right. So in lab yesterday, you guys got to kind of mess around with some of the stuff we were doing in class Wednesday, right? Talking about curved surfaces and making images from them, making both real images and virtual images. Yep. But you also talked about something we hadn't gotten to yet, refraction. We talked a little bit about refraction at the end of class last time, but that we just had barely gotten to it. So that's where we're going to pick up today. We're going to talk about refraction on a plane surface where it's just a flat boundary between two substances, two materials. And then we're going to talk about refraction on a curved surface. We've been talking about reflection and the law of reflection, how it's the bouncing of light rays off of something. And whatever the light ray is coming in at, that same angle from the normal will be what it goes out at. We talked about what that means for a concave mirror and a convex mirror. We made ray diagrams to represent where an image would be and what kind of image it would be and what that image would look like, whether it's upside down or right side up or bigger or smaller. And I gave you some equations that you can use to calculate those things. A few pieces of terminology I gave you. We talked about image distances and object distances, image heights and object heights. We talked about focal lengths for different types of mirrors. We're going to be doing a bunch of similar stuff, but this time for when light goes through something, not bounces off of it, but goes through. We'll also talk a little bit about something called a critical angle, total internal reflection, and fiber optics. And that's probably all the time we're going to have. A lot, right? A lot. But we can do it. We can do this. We have both ears, unlike Vincent van Gogh. He's only got one. All right? You got a Vincent van Gogh shirt on. Okay. What? Say what? Oh, you said that. Okay. Your shirt says 1977. It makes way less sense.
Yours says Mercy's University.
Yeah, I work at Mercy's. This is like a uniform.
What'd you have to say?
It says Equin Discs.
Yeah, you don't.
I'm sponsored by them. They give me stuff.
Really?
Like this hat.
Wow, that's pretty cool, actually.
Yeah.
You have an NIL deal?
What?
An NIL deal? Name, image, likeness?
Oh, no. They're allowed to use my name, image, and likeness on their site. Okay. So, refraction. We talked at the very end of class last time how if the speed of something changes, the direction of that thing tends to change too. I gave you a couple examples. We were pushing a lawnmower, it got off of the sidewalk into the yard, and it changed direction. You're driving in the wintertime and you get too close to the edge of the road, and your car gets pulled towards the ditch because it's changing direction because of that change in speed. That same thing happens when light goes from something to something else. Its speed changes. Do you happen to know off the top of your head what the speed of light in a vacuum is? It's one of those numbers that is probably on the equation sheet, but you probably aren't going to need to remember it because you'll just remember it by default. 3 watts. All right. Somewhere in here I've got a marker. I don't know where my marker is. We'll go with chalk. We're going old school. You said 3, right? So we use the lowercase letter c to represent the speed of light. And the number 3 is approximately the speed of light, but in a certain term. 3 times 10, it's actually 2.99 something, something, something. But 3 times 10 to the 8th in the unit, meters per second. 186,000 miles per second. That's a lot of miles. That's really far. 3 times 10 to the 8th is 3,000,000,000,000. A lot of zeros. The speed of light is really big. It's really fast. Specifically, this is a particular speed of light. This is the speed of light in a vacuum. Bless you.
What does that like even mean?
That's how fast an electromagnetic wave, a waving electric field or magnetic field, propagates through empty space. So if something happened to the sun right now, we would find out 8 minutes after it happened. It takes 8 minutes for the light that is emanating out of the nuclear reaction in the sun to get to us here on Earth. No, because the eclipse is the shadow from the moon, which is way closer. The speed of light, really fast. The distance to the sun, really far. Takes 8 minutes for the light waves, the wiggling electric and magnetic fields, to travel from that spot to here. Those flares we were seeing 8 minutes in the past. That flare where it was at. Now, is it going to change over a small course of time? No, because they're huge and they are moving really fast, but they're enormous and it's so far away. Even like huge changes don't look like big changes from that far away. It's like if you're in an airplane looking down at the ground, the little people don't look like they're going so fast, but maybe they're driving in their car really fast and you just can't tell because it's such a big thing that you're looking at, such a wide field of view.
And how do we predict things from the sun?
What do you mean? How do we predict something like the solar eclipse?
No.
With physics, with equations. Now, we didn't talk a lot about cosmology. I think I'm going to answer your question, even if I'm a little off base on what you're saying.
Yeah.
But we know the patterns. We know the laws by which the universe works. It follows the rules that we have established here in Physics 1 and Physics 2. And those rules let us predict forward and backwards. We can say this must have come from there, and it must be going to there because there are rules in place that it has to follow. So these things that I teach you, they're the fundamental rules of the universe and how it works. So that's like your question really gets to the heart of like all the people who have ever asked, why do I have to learn this? Well, that's one reason why. There's a lot of good reasons why. One of the reasons is you live in this universe, and this universe follows rules, and those rules are physics. That's our way of understanding those rules. Reason number two, it's problem solving, and in every career that you will ever encounter for the rest of your life, problem solving is an important skill. You will have novel information given to you, and you will have to interpret that information and make decisions based on it. That's what a physics problem is. It makes you do that. It's an exercise to build that skill set in your mind. So will you have to know that epsilon 0 is 8.85 times 10 to the negative 12th? No. Fun fact, part of the reason C is because 8.85 times 10 to the negative 12th is 8.85 times 10 to the negative 12th. Those things are linked together. The speed of light is dependent on how quickly electric and magnetic fields propagate through space. So they're all kind of related terms, but we don't need to get into that. That's just a fun fact to know. Whew. That's my my soapbox spiel. Thanks. It was a great question. So good job to you too. All right. That's the speed of light in a vacuum. Is it, since I'm saying speed of light in a vacuum, I think you can make an inference there. If speed of light in a vacuum is a specific thing, why do I differentiate it from other things? Why do I say a vacuum? Because it's different in other materials. Light propagates more slowly in other materials due to some relativistic physics in modern physics that we don't really need to talk about too much. We know that you cannot accelerate a massive object to the speed of light. Not possible. There's no rule to say you can't be going faster than the speed of light. And obviously light goes at the speed of light. And obviously we have things right now that are going slower than the speed of light. But you can't accelerate an object beyond the speed of light. So it's kind of like the speed limit for our known universe. So, speed of light in a vacuum, c, is the fastest it can be. When it goes through other materials, it must slow down. The speed of light in a material, we say, is just a velocity, v. The ratio of those two things, we call the index of refraction, n. And n equals c divided by v. When light moves through air, it's going ever so slightly slower than when it's going through a vacuum. But it's almost the same. It's so close, in fact, that we say that the n for air is 1. C divided by a number that is essentially the same as c is about 1. So n for air is 1. N for water is 1.333. N for glass is about 1.5. Different types of glass have different indices of refraction, but we'll call it 1.5. N for diamond is 2.5. Why do I remember these? Because I've solved a bunch of physics problems where I had to use them, and you stop looking them up after a while. It's faster to remember them. So tell me this, based on the information that I just gave you, if N for water is 1.333, is the speed of light in water faster, slower, or the same as the speed of light in air? How do you know? Explain the math. You're 100% right. So if C divided by V is N, and N is 1, that means C and V are the same. That's how you get 1 when you're dividing two things. How do you get a number bigger? You must be dividing by a number that is smaller, right? So V in water must be smaller. How about N in glass? It's about 1.5, maybe 1.52. You get different numbers for different types of glass. Faster, slower, the same. It's the slowest one of the bunch, right? I told you diamond. Do you remember what I said for diamond? Good memory. You do listen. I really didn't think so. And that's way slower, right? Much slower. That's part of the reason why diamond's so sparkly. It gives us something called total internal reflection, which we're going to talk about in a little bit. Okay, as a consequence of this, when light goes from one medium to another, where it's going faster to going slower, it's going to bend. Or similarly, if it's going from a medium where it's going slower into a medium where it's going faster, it's going to bend. How much it bends is determined by how much faster or slower it's going. So it depends on these indices of refraction. Let's say I have an air. This is air up on top. And this is water down here on the bottom. You can tell it's water because there's a fish. If I shine my laser at the water and it hits the water, some of it's going to bounce off. But some of it's going to pass through. Some will bounce off, but some will pass through. The amount that bounces off and the amount that passes through is a little bit more complex than the scope of what we're going to discuss. It depends on that angle, and the bigger the angle, the more bounces off, but that's for another day and another, perhaps, time. If the water wasn't there, the light would continue moving in this direction. It wants to keep going that way, but it hits that water and it changes direction. It slows down. When the light beam slows down, just like when I was driving in my car and the front right slowed down, it pulled me towards the ditch. When the light beam slows down, it gets pulled towards the normal. So it wants to keep going this way, but it doesn't. It gets bent towards the normal. So the angle, we'll call this theta 1, we'll call this theta 2. When it's slowing down, theta 2 will be smaller than theta 1. If it's going the other way, it bends the other way. If it's going from, in this case, air, and on top is air, and on the bottom is water, it's slowing down, which means it bends towards the normal. When it speeds up, it bends away from the normal. The mnemonic I learned when I was student teaching many, many years ago is Superman. Up, up, and away. When it speeds up, it bends away from the normal. You don't have to use my mnemonic. I like it because I like Superman. Reminds me of myself, both super and a man. So this is a surface of water, right? It's a pond. It's a flat surface. It's very calm. If it's ripply, then the normal changes, just like with reflection. But the fish is underneath the water. This is air. There's a cloud. it's up in the sky. Taking your laser, shining it in. Actually, I could literally do this right now because I brought water. I shine my light. I just put batteries in this thing. I shine my light in, it hits, some of it bounces off. It's not dark enough. Some of it bounces off, some of it goes through. You can see the beam in the water, right? No, I can. See it, am I lying? Can you see it? Yeah, you can see it. Let me ask you a question. This is a really cool question. You see the dot on the wall, right? The light is leaving my hand and going into that wall. Why can't you see it in between? How come you can only see the dot and not the beam in between? Because what?
We're not special.
You are special. That's not true at all. You are very special to me. Why can't you see the beam of light in between?
Going fast, man.
Yeah, it's going fast, but so is the light that hits the wall and bounces back. It's no different. The light between here and there is still an electromagnetic wave. It's still purple. It's still the same wavelength. Nothing about this that's coming out and that that's hitting the wall is any different. Why can't you see the light in the middle? Yeah, right now it's going from me to the wall, not to your eye. The beam is traveling that way, not this way to you.
When people have to like maneuver through laser beams.
Yep. Technically, you really wouldn't be able to see those laser beams. No, you never did. That's the whole reason I asked. Here, shine this at the wall, not at any of your friends. Let's see if we can get laser beams to show up.
What?
It's
like laser.
You can see it because it's got something to bounce off of. Can't say that's not cool, because it is. Super cool. But Nick, back to your original question. I'm shining my light beam into the water, the surface of the water. Normal to the surface of the water is straight up and down. No.
Nick hates lights.
Lights are coming on. I find it very soothing to have the lights off.
That's like
all right,
too
so
dark, though.
you were scared? You have friends in the room. Everybody's friendly here. Don't be scared. We'll protect you. All right. So you got a surface. You got a flat surface of the water. I shine my laser in at it. The normal to the surface is straight up and down because the surface is flat, right? Normal means perpendicular to. That's perpendicular. So compared to the normal, we have this angle right here as the light's shining in. So far, so good? If there was no surface, it would just keep going straight. But it doesn't keep going straight. It slows down, so it bends towards the normal. It wants to go this way, but it can't. It bends towards the normal. The normal is straight up and down. It was this way, it bends towards it. Is my interpretive dance helping? Okay.
So it'll always bend towards the normal?
Only when it slows down. If it's speeding up, what does it do? Away from the normal. So here's the water, the surface of the water. The light beam is coming out. I'm scuba diving with my laser because I don't want to leave home without my lucky laser. I want them to be able to find me, so I'm shining the light out of the water. So shining my laser this way. If there was no boundary there, it would just keep going straight. But there is a boundary there. It speeds up because it's going from water into air. When it speeds up, it's going to bend away from the normal, which is, if this is the normal, it bends away from the normal, like so. Yeah? I can show you that too, but Nick, you gotta bear with me while I turn the lights off again. I'm telling you, don't be scared. We'll protect you. I'm teasing, you know I'm teasing you, right? Oh, yeah. All right, okay. You don't seem like a sensitive type. So I got my light beam. It wants to go in a straight line. I bring my piece of plastic and it doesn't go in a straight line. Notice that it wants to go this way, but it gets bent. As it goes from the air, N of 1, to the plastic, 1.5, it bends, it slows down and bends towards the normal. If you don't believe me, I'll pass this around. You can actually do it on your desk and you can see it. When it leaves on the top side, when it's going from the plastic back into the air, it bends back away from the normal because it's speeding up, up, and away. You can put it on your desk. You can see both times where it's bending. Can you see that? Yeah. Okay. Sometimes it's hard to tell. I can see it because I'm right in the front. Pass that around. Don't drop my big piece of plastic. Those are hard to replace. Nick, you all right back there? Okay, I'm going to turn the lights back on. You made it. Be brave. How much it bends depends on how much it speeds up and how much it slows down. And how much it speeds up or slows down depends on the difference between the n values. We have an equation for that. I don't remember if I gave you the equation last time or not, but I'm going to give it to you now. It's called Snell's law. Snell's law says that n1 sine theta 1 equals n2 sine theta 2. I can turn some of the lights off if it makes it easier. You can't see it in there with the lights on. I don't know. No, that's more light. That's more light. I don't know. That's all the lights. It's all or nothing, folks. It's all or nothing. You know what I can do? Nothing. I can do nothing. I can't do anything. I was thinking I could turn the screen on, but it's not going to help. It might help. Could you? All right.
You got those lights on. Hit that one and then turn those ones on.
Maybe. Maybe. N1 sine theta 1 equals N2 sine theta 2.
Oh.
Sweet. I feel like I'm on stage. This above all to thine own self be true. Whether 'tis novel or 'tis something the slings and arrows, something, I don't know, I don't remember.
You got it.
Okay. N1 is the index of refraction of the medium that it's coming from. Sine theta 1. Theta 1 is the angle compared to the normal on the incoming side. N2.
Slow down. Angle compared to...
I'd rather you just understand it and write down N1 sine theta 1 equals N2 sine theta 2, but if you want to write it, that's fine.
Angle compared to the normal.
Yeah.
And then what was the N1 index?
Index of refraction of the material that it's coming from. N2 is the index of refraction of the second material. It's going from something into something. Theta 2 is the outgoing angle, the refracted angle, compared to the normal. It's always compared to the normal. Both reflection and refraction always compared to the normal. So I want to put a couple things together. I brought some toys to play around with and show you. We couldn't see the laser beam because there was nothing in between the laser and where it was going, its destination, to reflect it to your eyeball. Refraction kind of does the same thing. If I tried to spear that fish in my drawing, and I aim where the light is coming from, where my eye interprets the fish as being, I'll miss the fish. I won't be able to hit the fish because the light coming from the fish gets bent before it gets to my eye. So here's the water. Here's me on a boat. Where? I'm going to spearfish this fish. There's the fish. I see the fish because light bounces off the fish and gets to my eyeball. But when it goes out of the water, it bends, it speeds up, so it bends away from the normal. So the light is actually going like this and then bending away from the normal and getting to my eye. So if I actually am looking where I think the fish is, that light looks like it's coming from here. So if I throw my spear where it looks like the fish is, I'm going to miss. Our vision is an interesting thing. How we interpret the light that we see is a really interesting thing. Refraction, like reflection, can give us some really interesting phenomena like this one. So this is water. This is a light bulb. The light bulb is made out of glass. The index of refraction between the air and the glass of the light bulb, the difference between them is bigger than the difference between the glass and the water. So light will bend differently. It'll actually bend more when it hits the bulb and comes to my eye compared to when it's in the water, because the air is what it's going through instead of the water. The difference in the two mediums, the surface between them, the change in N is bigger right now than it would be if I put it in the water. So when I put it in the water, it's going to look differently in a really cool way. You ready for this?
Oh.
Yeah, whoa, look at that. Isn't that cool? I'm going to turn the light on just so the people in the back can see it a little better. Now that I know I can do this stuff. So it just looks like a normal light bulb until you dunk it in the water. And now how the light is bending before it gets to you is different. It bends less. It's harder to see. Normal light bulb, dunk it, it doesn't look normal anymore. Yeah. It does. Normal? Abnormal. Isn't that cool? And it actually works. So we see the glass less, and we see the powder coating on the inside more. You can do the same thing. I didn't know if you could. I just grabbed this to try it. And you can kind of see it the same thing for the glass on the outside. It's not as obvious though, because it's, I don't know, the angles are different. But I also brought what I hope is going to work as a magic trick. I don't know if this is going to work. I didn't get a chance to try it beforehand. I borrowed this from the chemistry department. I got this out of the physics lab. This will work better if I only do it once, so everybody come up to the front, please. The index of refraction for the vegetable oil in the Pyrex glass is very similar. Now, when I put the glass in the liquid, it looks a little funny, but you can still see it just fine. But if I fill the glass with the oil, it disappears. Now, you can see it, it's here. You can see it when it's underwater. When I fill it with the, or when it's under the oil, when I fill it with the oil, gone. Isn't that cool? Now, if you come close, you can still see it. You can see the outline of it, but you certainly can't see it as well, because the light doesn't refract as much. It doesn't bend as much when it gets to you, and that light doesn't actually get to you. You don't interpret it as being there. I think that's the coolest thing.
The coolest thing ever?
One of the top 5.
Really? What's one?
I don't know. I got to think about that. That takes a little bit of effort.
Yeah.
What?
I'm just talking
Really? Oh, hey, look. Geometric optics. Oh. We were doing this. Look at that. I didn't realize they had one of these. That's not the one I'm looking for. Oh my gosh, where's the one I'm looking for? I know it's in here. I was playing with it yesterday. I did. I found it for the second class.
Oh. Well, we should probably watch it. I thought about it until now. I feel like that's pretty important.
We don't have time to watch it right now. I could send it to you if you'd really want to see it. I'm happy to share. When I send a laser into the water, it's starting in air with an index of refraction of 1. It's going into water with an index of refraction of 1.333. And some of it, as I said, hits and bounces off, and some of it bends. If it wasn't going through water, it would just keep going in this direction, but it doesn't. It bends this way. It slows down, and it bends towards the normal. As I change my angle, this outgoing angle changes too. It still wants to go that way, but it's coming out this way. It changes with it, but at a certain point, I can't go any farther, right? Like I can't go any farther down than exactly parallel to the surface. Yeah. Yep. I don't know the index of refraction for salt water, but it does. Look it up. Check it out. I don't know. I'm pretty sure ice bends light differently. That's why when you put ice in the water, you can still see it. It's not invisible. If I'm going from air, here, let's put our protractor there so we can see the angles. I'll make the beam coming in at 30 degrees from the normal, and notice that it is not leaving at 30 degrees from the normal. It's a little bit less. It bent towards the normal. This angle is smaller than that angle. Is this kind of helping clarify what I'm talking about when I say towards the normal, away from the normal? All right, good, perfect. If I switch from water to glass, the index of refraction gets bigger, so the difference is bigger, so the bend is going to be bigger. So where will the beam go when I switch this to glass instead of water? More towards the normal. It's going to bend more. You got it. So, yep, water, it's at about 20. Glass, it's at about less than 20. 18, 17. What are you asking me?
I'm checking.
Normal is perpendicular to surface?
So did it-
Yeah, it's just showing you where the normal is.
Okay.
That's not part of, it's just like a reference for you to know what normal means. Because you're fairly abnormal and some people don't know what normal is. It's a sick burn, but no one got it. If it's going from air to air, the angles are the same. If it's going from air to, or from water into air. Now, we're kind of looking at the world upside down. The water's up on top, the air is down here on the bottom. It's like you're looking at the pool upside down like so. My laser's under the water, it's going at 30, but it doesn't come out at 30. It bends, it's speeding up, it bends away from the normal. The relationship, n1 sine theta 1 equals n2 sine theta 2. Why don't we just try a couple for the practice, and then I want to show you something in this scenario where an interesting phenomenon happens. One that you actually have seen many times before, but you might not have realized what you were seeing. Okay, pick a number between 1 and 90 degrees. Between 1 and 90, that's, you said 36. So I'm going to shine my light ray in at 36 degrees. I'm in water, I'm going into air, I'm shining my light ray at 36 degrees. Yeah. What will the outgoing angle be? Find it. I just got an email. Nope, this scenario right here. We're underwater, we're going into air. In this case, what is N1? 1.333. What is N2? What does that 36 degrees represent? Theta 1. And what are we trying to find? Is it going to be bigger than 36 or smaller than 36? Okay, so in my sketch, I'll make it a little bigger. How are we going to find it? That equation right there. So we know several things. We know N1, we know theta 1, we know N2. The only unknown is theta 2. So we're going to try to find theta 2. N1 sine theta 1 equals N2 sine theta 2. Doing our algebra, what's the first step? What am I going to do? Solving for theta 2, what's the first step? Sienna, what? Divide, you're right, divide what? Yeah, divide N2 over. So we end up with sine theta 2 equals N1 divided by N2 times sine theta 1. And how do I find theta if I have sine theta? What's the opposite function? Inverse sine, yep. So we're going to take the inverse sine of both sides, and that'll give us theta 2. Theta 2 equals the inverse sine of N1 over N2 times sine theta 1. Sydney, you give me an answer? Is that what anybody else got? Also got 51? Sean said you got it. Let's find out. Let's put this to 36. And what are we getting? What's the angle? Is it, you get an error, you're probably in radian mode. I'm going to double check your numbers just to be sure. N1 is 1.333 divided by N2, which is 1. That's 1.33. That answer times the sine of our incoming angle, which we said was 36. That's the inside part. Now I'm going to take the inverse sine of my answer there. I do have it in degree mode. I do. Good. Equals 51.6. Rock and roll. Sweet. Nice job. How come their number on the simulation didn't quite jive with our number? I don't know if you noticed, but it wasn't quite the same. It was similar. It was close, but it wasn't quite the same. No, it does reflect, but that's not, that doesn't affect the refraction. Do you look at the n value on the simulation? They use a slightly different n value, which means we'll get a slightly different output. As long as you use the given values that I tell you, and you do them the way you did, awesome, you're gonna get it right. You wanna try another one, or are you pretty comfortable with that? You wanna do another one? Okay. You wanna try a different set of materials? Give me the scenario. 78 degrees, okay. We're gonna go down here to 78. I'll set it later. So 78 degrees coming in. What material is it going from and what material is it going to? Air into glass. So we'll set it to air and we'll set it to glass. So air is going into glass at 78 degrees from the normal. It's kind of like looking through a window. Right? Light's coming in and it's going out. We're shining my light through the plastic. It's going from air at 78 degrees. So 78 degrees is a pretty steep angle, like this. 78 degrees. Is it going to bend towards the normal or away from the normal? Towards the normal. So it's going to be smaller than 78. We expect our answer to be smaller than 78 degrees. How much? I don't know. We're going to find that out. What's N1? What's N2? We should get the same answer this time because we're going to use the 1.5 that they're using. Did you ever find out what the N for saltwater was? That's what you got here? 40.7 degrees? Is that less than 78? Does that make sense? Yeah. One more time. What was the number? 40 point something? All right, cool. Let's find out. Let's put it on the sim. That's 73. Somewhere in here. Yeah, it's just almost exactly 40, but slightly above. That's great. Nice job. Because this is 30, that's 35, that's 40. It's just ever so slightly more than 40. Rock and roll. Not so bad, is it? 1.9. Holy cow, that's a lot bigger. Who knew? Now we do. We're the ones who know now. Okay, I want to show you something kind of cool. If you're going from one medium that is slower, and you're ending up in a medium that's faster. You're speeding up and you bend away from the normal. Now, in this case, I can never go far enough down. Once I get close to the surface, it's always going to bend towards the normal, so it's never going to reach that surface until like none of the light actually crosses. But if it was bending away from the normal, like when it slows down, like if I was going from glass into water, there's going to be a spot where I have moved this close enough. I've got a big enough angle here that none of the light is going to actually get through. The outgoing angle is going to reach 90 degrees before the incoming angle does, because it's bending away from the normal. At that point, right here, right there, none of the light gets out. The outgoing angle is 90 degrees, which means none of the light escapes, which means that all of the light is going to reflect. It's going to bounce off. You've probably seen this before. When Joey was little, we used to go to Jasmine Thai restaurant in Buffalo. It's my favorite Thai restaurant. It's right by North Campus. If you're from Buffalo, you should check it out. It's really good. In that restaurant, it's a little hole-in-the-wall kind of restaurant. They got a fish tank with this like weird-looking fish in it. And Joey would, as a little boy, he used to go look at the fish while we were waiting for our food. And sometimes when he was standing on one side of the fish tank, I could see him perfectly. It was like looking through a window. But then he would go around to a corner of the fish tank and I couldn't see him anymore. That side of the fish tank looked like a mirror. But if I moved and looked at it from a different angle, I could see him again. I could see through it just like a mirror. You've probably seen this before, and you can see it when you look through any surface where the light is going to be doing what I described. When I look through this cube, I can see my hand, but then I turn it a little bit and I can't see my hand anymore. It looks like the inside is mirrored. But then I turn it a little bit more, or I change how I'm looking, and then I can see through it again. When this happens, it's called total internal reflection, because all of the light is reflecting. Total internal reflection. And the angle where that happens is called the critical angle. The critical angle is the angle at which you reach total internal reflection. None of the light gets out. It's bright enough you can see just fine. All right, so I'm shining my light into the surface. Some of it's getting out the other side. You can see the light shining up on top, right? Can you guys see that? If I come in from this side though, can you see the light coming out the top? You certainly cannot, because none of it is. See how it's bouncing on the inside? If you put your hand up here, your hand will not get any blue light on it at all. Here, blue light's coming out. Here, none. Total internal reflection. If we were to design a material that had a diameter or a width that was smaller than would allow for the angle to be small enough to let the light escape, that light would be trapped inside of that like tube for light. In fact, I brought one. This is such a material where the index of refraction does not let any of the light get out. It can go around the corners. It doesn't matter how it's bent. All the light that I put in is going to come out the end here. If I was to like align that with the projector, I'd be able to see what the projector was showing through the little end of this nub. This is how fiber optics work. It's a tube for light. You can transfer energy through this light tube at the speed of light. That's why fiber optic cables are so fast for their data transmission. I've got a thinner one that might be even more obvious. You see the tip is glowing blue or purple? Because the light can't get out. It's totally internally reflecting inside of this. Yeah, the same thing. It's because of the difference in index of refraction between the material and the air around it, as well as the small diameter of the tube. It's not really a tube, it's not hollow, but it's like a tube for light because it carries the light beams inside of it all the way around. And it doesn't matter if I can twist it all the way around. It won't matter. It'll still come out the end. See it? And yeah, kids' toys, they make kids' toys out of these. We can calculate the critical angle at which total internal reflection takes place. That's the last thing I'm going to show you, and then we're going to be done for the week. Lights coming on. Okay, we're going to use Snell's law. In this case, this index of refraction of the material we'll say is glass, n equals 1.5, and it's coming from air, n equals 1. We have light coming in. The outgoing light ray is not getting out, which means the outgoing light ray angle is 90 degrees. This angle that it's coming in at, where that happens, is the critical angle, theta sub c. So I want to solve for theta sub c. Theta 2 is 90 degrees. So I'm going to go over here to my Snell's law equation. N1 is 1. Theta 1, we don't know. It's the critical angle, theta c, equals N2, which is 1.5. And sine theta 2 is sine of 90 degrees. What's the sine of 90 degrees? 1. So the sine of the critical angle equals 1.5 divided by 1. The critical angle theta is going to equal the inverse sine of 1.5. What is it? You got a calculator? What's the inverse sine of 1.5? Are you in radio mode?
I also done.
Remind me, we have to pick up here next time. We rush through it. This is what we'll start with next class. Monday? We're out of time.